In this video, we'll see an efficient algorithm for training a restricted Boltzmann machine known as contrastive divergence. So we've seen the restricted Boltzmann machine, how it defines a distribution over X and its hidden layer H. We've seen that we could also write down P of X using the free energies, and we've looked at how exactly it tries to model an increased probability for certain values of the input vector. Let's actually see how we can actually train a restricted Boltzmann machine on some training data in order to obtain a restricted Boltzmann machine that models well that data and assigns high probability to it. So, like we've seen before, we'll treat this problem of training as an empirical minimization problem. We'll do without the regularization here and just try to minimize the average loss, where the loss is going to be the most natural thing here to do, which is to use the negative log probability as our loss for this model. And so what we'd like to do is optimize this average negative log probability of the training data using an optimization procedure. In particular, we'd like to use stochastic gradient descent because it works well and it scales well to large data sets. And so it means that to achieve this, I need the partial derivative of any parameter theta of my loss. Now, if I make the derivation and write down the expression for it, it actually has an expression which looks kind of similar to other things we've seen before in terms of partial derivatives of parameters for neural networks. We have again a difference of two terms, one which depends on the observation and another one which depends on more explicitly only on the model. And so this partial derivative is going to be the expectation over what we never see, which is the hidden layer value, of the partial derivative of the energy with respect to my parameter given my observation. So an expected partial derivative. We have to do an expectation because h, we never know what its value is. And so it's the expectation of this partial derivative conditioned on the observation. And then we subtract to that the expectation over h and now also x of the, again, the partial derivative of the energy function with respect to our parameter. But notice now we do an expectation over x as well, and this is an expectation according to our model, so under our model's distribution. So we often refer to that part, computing this part of the gradient, as the positive phase and this the negative phase for obvious reasons. And but now the problem is that this part here is actually hard to compute. It's generally intractable, and the reason is that we have to make an exponential sum over both h and x. And so perhaps you'll be convinced that if I give you a value of the visible layer, so if I give you an observation x, then summing over h is actually something that's tractable to do for this partial derivative, in particular for the RBM. Indeed, we can again leverage the fact that we get an expression of nested sums over something that factorizes with respect to each hidden unit, and then we can actually write this down into an expression that's linear in the number of hidden units. So we'll see that more in more details later in this video. But now if you have to do a sum over both x and h, now this becomes intractable. And so we'll have to approximate that term somehow in order to perform stochastic gradient descent efficiently. So to address this problem, Jeff Hinton in 2002 proposed the contrastive divergence learning algorithm. So there's some theory for what this is actually doing. I'm not going to go over that. I'm just going to describe what the algorithm is in the more intuitive terms and try to give more intuition for why it should actually work. So really the idea is to try to do without this double expectation and instead estimate it. So there are really three main components to contrastive divergence. The first idea is that the expectation over x and h in the negative phase will actually replace it by a point estimate at a single observation x tilde. So the expectation over x will replace it by a point estimate at x tilde because if we have that point estimate, if we give me a value of the visible layer, then I can do the expectation over H and then get an estimate of the double expectation. So that's just really saying we'll do Monte Carlo estimate of the expectation with a single data point. Then we need to obtain that X tilde somehow. And ideally, we like to sample from the true distribution, not the true distribution, but our model distribution. And then we'll do this by Gibbs sampling. So remember that Gibbs sampling corresponds to sampling each variable in my model given the others. And specifically for a restricted Boltzmann machine, performing that sampling is actually quite efficient because conditioned on one layer, all the other elements in the other layer are independent. Then I can sample all the values in one layer in parallel given the value of the opposite layer and then alternate between each layer like this. And so this is actually very efficient to do in practice. And then the third idea, which is perhaps the most important contribution behind contrastive divergence, is to perform Gibbs sampling, but by starting our sampling at a state where the visible layer is set to the training example for which I'm trying to compute the gradient and do an update. And so instead of starting like we usually do in Gibbs sampling at a configuration of my my layers, my random variables that is sampled perhaps uniformly and just randomly according to some initial distribution, I'll actually use the value of the training observation for the value of the visible layer when I'm performing Gibbs sampling. And the other thing is that I'm not actually going to do Gibbs sampling for long. I'm actually going to do it for 1, 2, or just a few iterations. And as we'll see, this actually works well in practice. So to illustrate this process more visually, so there's a little error in my figure. There should be the same circle here. So what we'll do is that at training time, for a given training example, I'll take the value of the input vector x, and I'll set it as my value for my visible layer. Then I'll sample all the hidden units, conditioned on observing this particular value of the visible layer, this training example. So I'll sample from P of H, given that X is equal to XT in this case here. Just a note on performing that sampling. So each neuron on conditionally independent, so they're each a Bernoulli for which I can compute what's the probability for that Bernoulli random variable, that hidden unit being equal to 1 given X. Now, to obtain a sample from a Bernoulli with that probability of being equal to 1, what I can do is just sample from a uniform distribution between 0 and 1. And then if that value, that uniform value that I sampled is actually, sorry, it should be the other way around. So if this value is greater than the value, the probability is greater than the value I've sampled from my uniform, then I'm going to set the hidden layer unit, the jth hidden layer unit, to 1, and otherwise I'm going to set it to 0. So in other words, the value of the hidden unit is going to be the identity function of whether the probability of the hidden unit is greater than a random sample from a uniform between 0 and 1. So we can see that this will be equal to 1 with a probability of this value because the mass of a uniformly distributed random variable between 0 and this value is going to be exactly, because it's uniform, it's going to be P of Hj equal to 1 given X. So indeed, the probability that this is 1 is going to be P of Hj equal 1 given X. Okay, so now I've taken my training sample, I've sampled each of the hidden units, conditionally conditioned on the visible layer taking that value, and then I'm going to reconstruct the visible layer by sampling from P of X given the current value of my hidden layer. So I could call this a X1. And then I'm going to do that for k steps. So I'm going to take x1 and then sample a new value of the hidden layer given my previously sampled value of the visible layer. I'm going to alternate like this, performing Gibbs sampling for k steps. And now this last value, after I've done my k steps, is going to be the negative sample x tilde. So x tilde, we often refer to it as a negative sample, which is used to estimate the negative phase part of the gradient. And so I'm going to use that as my negative sample to perform my point estimate of the expectation over x. Okay, so visually, what does this look like? So I get a training example, and in the positive phase, I'd had to estimate this conditional expectation. To simplify, imagine I actually don't perform that expectation. I just sample an h given this xt, and I'll call that h tilde t. And I've also performed k steps of Gibbs sampling, so I have an x tilde, and similarly, to perform that expectation, I'll estimate it at x tilde and h tilde, where h tilde would be sampled based on the conditional distribution of the hidden layer given that x is equal to x tilde. So then I get these two pairs, and if I look at the gradient descent procedure, what it's telling me is that I should decrease the energy at the training observation, and I should increase it at the sample value x tilde in its associated hidden layer. Because low energy means high probability, then this means that I'm going to increase really the probability of observing xt with its hidden layer, and I'm going to decrease at the same time the probability that x tilde is going to be observed under my model's distribution. And so if my training example corresponded to images of digits, then I'd be increasing the probability of observing this particular digit here under my model. And then say initially my restricted Boltzmann machine is randomly initialized, so it essentially corresponds to a uniform distribution over binary vectors. Then initially what I'm going to sample is really going to look like noise, essentially. It's going to look like something like this. And so what I'll be doing is then making the probability of sampling something like this from my model much smaller. And then I'll continue iterating like this. So next time around, it'll be less likely that x tilde would look like a random image, and the sample value for x tilde are going to be looking more and more like actual training examples, because I keep pushing down the probability of anything that doesn't look like a digit. And so we can see that as we keep sampling like this, then eventually the gradient should become smaller, because the value of xt is going to be more and more similar to the sampled value of x tilde. And so intuitively, this algorithm, what it's doing is that it's increasing the decreasing the energy of things that look like what's in the training set, while increasing the energy of things that are hallucinated or sampled by the model. And we keep doing this until the model spits out or generates observations that are very similar to what's in the model. In other words, it's become a good model of our data set.